Heat, specific latent heat, 2011 question 7 and higher level, centred around a question that involved adding a steam to a hot drink to obviously bring the temperature from 20 up to 70. So what we're looking at here in this question is, again, marking out all of the parts. So A is looking for the mass of the steam. Okay, and again, it says ignore the energy losses to the surroundings. And then it also says, well, what is the heat capacity of the spoon? And again, ignore other possible heat transfers. So we have two parts of this question in the calculation. Then in B, we're just looking for how is the energy lost, and C, we're looking for how would you demonstrate. So again, there's two parts to this. So again, always breaking down our question, how many parts are there, so that we can tick them off as we have them done to make sure we haven't missed any possible questions. Okay, so let's look at the first part of the question then. So in A part 1, what does it want us to do and what is it giving us? So it says we're making a hot drink and we're adding steam at 100 degrees Celsius to 160 grams of milk at 20 degrees Celsius. And the final temperature of the drink is 70. And we want to know what mass of steam should be added to raise the temperature of the milk from 20 to 70. So what's happening? So we're basically going to have heat loss equals heat gain. And again, it doesn't matter if you write this the other way around. What's losing the heat? Well, clearly the steam. What's gaining the heat? Well, it's going to be the milk. And we're not told anything about the container that contains the milk. So is it a polystyrene cup? Is it a copper cup? Is it a glass cup? We don't know. So again, we're told clearly to ignore energy losses to the surroundings. So nothing else is relevant for this particular question. So it's literally just the steam being added to the milk. Okay. So down here at the bottom then, we have specific heat capacity for milk, specific heat capacity for water, specific heat capacity for a hot drink, and specific latent heat of vaporisation for water. Okay, so we're given all our constants at the bottom of the question. So what's going to happen to the steam? Well, if we look at the steam is starting at 100 degrees and yet the final temperature is 70. So clearly that means that the steam is going to change state. So that'll be ml plus it's changing its temperature because the final temperature is 70 degrees. So that's going to be mc delta theta. So when we have a change of state, it's always ml, and when we have a change in temperature, it's mc delta theta. ml being the energy needed to change its state from steam into water, and mc delta theta, the energy needed to bring its temperature down from 100 to 70. So m is the mass of the steam, L is going to be vaporization because it's condensing, m will be the mass of the steam, and C will be the specific heat capacity. Well, it's going to change from steam into water, and then it'll be the change in temperature of the steam. And then that's going to be equal to the heat gained by the milk. So the milk starts at 20 and ends at 70. So there's not going to be any change in state here. So it's just going to be a change in temperature for the milk. So it'll be the mass of the milk, specific heat capacity of the milk. You can see we're given that, and the change in temperature of the milk. So let's put in our values. Now we have to be careful here because I'm going to do this to the side because I can see my mass is going to be given to me in grams. So we have the mass of the milk is 160 grams. So if I divide that by 1,000, that's 0.16 kilograms. Mass of the steam is what we're trying to find. We don't know. Change in temperature of the milk. Well, it starts at 20 and ends at 70. So its change in temperature is 50 degrees Celsius. And change in temperature of the steam. Well, the steam starts at 100 and ends at 70. So its change in temperature is 30 degrees Celsius. So subbing everything into our equation here now. Mass of steam we're trying to find. times the latent heat of vaporisation. So I can look at my constants here at the bottom of the question. So that's going to be 2.34 by 10 to the power 6 joules per kilogram. Plus mass of the steam. So again, we're trying to find that. Times specific heat capacity of water. So that's 4.1 by 10 to the power of 3. So again, 4,180. By the change in temperature of the steam, which is 30. And that equals the mass of the milk, 0.16, by the specific heat capacity of milk, and I can see that that's 3.9 by 10 to the power of 3, so 3,900, and change in temperature of the milk is 50. Okay, so let's simplify that. So again, I can see mass of the steam here is common on the left, and that's what I'm trying to find. So I'm going to take that out as being common. And then what am I left with? Well, I'm left with 2.34 by 10 to the power 6 plus 4.18 by 10 to the power 3 times 30, which is 125,400. And then that equals, on the right hand side, if we multiply it out, 31,200. So on the left hand side, then we have the mass of steam times 2.4654, and that's by 10 to the power of 6 equals 31,200. And then dividing both sides across by 2.4654 by 10 to the power of 6 gives us 0.1266, and that would be kilograms. Okay, and it is only looking for the mass of the steam, so we don't have to say what it is in grams or anything like that, so we'll stick with kilograms. And if we look at the breakdown of the marks then for that question, what have we got? Well, we have 6 for our equation. So basically, if you look at that equation, there are 3 parts to it. So you'd have 2, 2, and 2, right? So any of those missing, you would have lost 2 marks, okay? Then if we look at the next thing we had to do was sub in all of the correct values. I missed something there. So 3 for substitution, and then 3 for getting the mass of our steam. Okay, so the next part of the question says, then what is the what is the heat capacity of the spoon, not the specific heat capacity, given that the metal spoon has an initial temperature of 20, it's placed into the hot drink, and it causes the drink's temperature then to drop to 68 degrees. So again, we have to say, well, what is actually going on here in this question, first of all? Well, clearly we have heat gain is equal to heat loss. And again, you can write heat loss equals heat gain, it doesn't matter. So what's gaining the heat? Well, clearly the spoon must be gaining the heat because it causes the temperature of the drink to lose its temperature. So the temperature drops. So the hot drink is losing its temperature. Now let's look at the temperature. So the temperature is going from 20 for the spoon to 68 degrees. And therefore there is no change in state. So it's literally just a change in temperature. So we're going to have change in temperature, so MC delta theta equals change in temperature for the drink, so MC delta theta. So we're going to have mass of the spoon. But again, if we go back, it's no mass of spoon has been given to us. And therefore that's, again, let me just double box this, is heat capacity. So again, if we go to our tables for our heat capacity on page 58, you can see that we don't actually need our mass. That's our specific heat capacity. So I have to change my formula there to just C delta theta. And again, that's a capital C. So let me overemphasize that. So it's capital C for heat capacity of the spoon. I'll do right spoon as opposed to S for steam. And then the change in temperature for the spoon. And then it's going to be the mass of the hot drink. So I'll do H for hot drink. Specific heat capacity. Now again, go back here, look. It actually gave us a specific heat capacity for hot drink. So we don't have to do milk and water separately. It's given us the combination there for this question. So hence this is a question I'm using for an example because it's an interesting one in terms of the values given. And again, we're looking for each of our values before we start the question. So let's have a look. Our heat capacity of the spoon has been given to us. No, is what we're trying to find, sorry. Our change in temperature of the spoon. Okay, so what did the spoon start at? Well, it started at 20 and it ended up being 68. So we have 68 minus 20 is going to be 48 degrees Celsius. If we're looking at the mass of the hot drink, well, the mass of the hot drink, what do we know? Well, we know that we had, let me go back. We go back up here. So we have 160 grams of milk, and then we worked out the mass of the steam is 0.01266 kilograms. So therefore the mass of the hot drink must be the mass of the steam plus the mass of the milk. So the mass of the hot drink, well, the mass of the steam was 0.01266 plus the mass of the milk was 0.16. So that gives us the mass of the hot drink to be 0.17266. Okay, and then we have, again, our specific heat capacity of the hot drink is given to us. So the change in temperature of the hot drink, well, it starts at a temperature, if we go back up, the final temperature of the drink is 70. So it started at 70 and it drops to 68. So it's dropped by 2 degrees Celsius. Okay, so now we have all our values worked out. We can now sub it into our question. So our specific heat capacity for the spoon, I'll just shorten that to SP for spoon, times the change in temperature of the spoon, we said is 48 degrees Celsius, is equal to the mass of the hot drink, and that should be kilograms over there, is 0.17266 kilograms, times the specific heat capacity for the hot drink. Let's go back. So that's 4.05 by 10 to the power of 3. Times the change in temperature of the hot drink is 2. So in other words, we have 48C for the spoon is equal to 1,398.706. And if I divide that then by 48, we end up with 29, I'll do it correct to 2 decimal places, 0.14, and that's joules per Kelvin for our heat capacity. And again, if you can't remember your heat capacity units, again, you need to go to the back of your tables. And for heat capacity on page 66, you'll find your units. Okay, so just star that, units, page 66 in your maths tables. Okay, so the breakdown of our marks there then, again, we had 3 for saying that our heat loss is equal to our heat gain for the spoon and the drink. So implying that you could get 3 marks. And again, 3 for our formula, 3 for substitution, and 3 for answer. And of course, if you've no units, you'll lose 1 mark at the end of that calculation. Okay, so B. So let's go back. So B says, name 2 processes by which a hot drink cools, and how is the energy lost by each of these processes reduced when it's applied in a disposable cup. So if it's a disposable cup, how can we reduce these heat losses? Okay, so the 2 processes by which the hot drink cools the first one and the second one. So we'll have convection, because it's a hot drink and it's a liquid. And with liquids, what happens is obviously you'll have the heat rising. So to prevent that from happening, we would use a lid. Okay. And of course, if we have like a cup, what can happen is you can have conduction through the container. So again, to prevent conduction through the container, what you would want is a cup made from an insulating material such as polystyrene. Because that's an insulator. Okay, and that would prevent conduction. Now you could also say radiation, because you can have heat loss through radiation as well. So any hot object will radiate heat. And of course, to prevent that from happening, you'd want a shiny inside the cup. And a lid. Okay. So we only needed two. So convection and conduction would be the two I'd give there for my answer. Okay, so see then the last part of the question. Oh, sorry, there was 4 for giving your 2 processes and then 3 for giving the reason. So we had 4 marks and 4 marks and then 3 marks and then 3 marks. That was a really, really handy set of 14 marks. So C then was a thermocouple is used to measure the temperature of the steam. How would you demonstrate the principle of the operation of the thermocouple? And then describe how to establish a calibration curve for a thermocouple. Okay, so let's have a look at the diagram of a thermocouple first, and then we can explain it with the diagram. So if we go to page 135 in our textbooks, we have a nice diagram. And again, in the Leaving Cert, I would draw this diagram to help me explain how the principle of operation of the thermocouple works. So essentially what you have is you have your 2 metals. So you have your copper and your iron joined together. And then what you have is one junction is at a fixed temperature and the other junction has a varying temperature. And then when that happens, what happens is you get a small EMF on your voltmeter. And then that's able to be measured. In other words, it changes measurably with temperature. So we say we have 2 different metals. Joined together to form a complete circuit, as in the diagram. And we have one junction is kept at a fixed temperature. Which is generally our cold junction. So maintained at 0 degrees. And the other junction is heated and an EMF appears in the circuit and is measured with a sensitive voltmeter. Okay, so we had basically 3 marks for talking about our fixed temperature cold junction. We had another 3 marks then for our varying junction temperature, and then 3 marks for our observation. What do we actually see? So that was part 1. And part 2 then says, well, describe how to establish the calibration curve for the thermocouple. So for the second part of the question, how are we going to establish our calibration curve? So we take our diagram and again redraw it, and just to have our cold junction, which will have our melting ice, which is our maintained at 0 degrees. And then to vary our current, well, we have to show, sorry, not vary our current, vary our temperature. What we need to do is place the second junction in a beaker of water and heat it. So you can either use a hot plate or a Bunsen to cause that temperature to change. And of course, we need to measure the change in temperature to plot a calibration curve. So we either need a digital thermometer, a data logger, and a temperature sensor, or just a normal standard lab mercury thermometer. So how are we going to set this up? Well, the first thing what we want to do is we want to maintain one junction at 0 degrees Celsius in a beaker of melting ice. And then we have the second junction in a beaker of water. With a thermometer. So again, if you've labelled data logger and temperature sensor, then you'd state that here. So I've drawn a mercury thermometer. So a junction with a beaker, well, I've probably drawn an alcohol thermometer because I've coloured it in red, but it, again, doesn't matter, you can colour it in whatever way you want there. So place the second junction in a beaker of water with a mercury thermometer and heat the junction in approximately steps of 10 degrees. And obviously it won't necessarily be 10 degrees once you stir the thermometer and wait for the temperature to settle before taking your readings. Obviously, because you'll have an uneven distribution of heat there, so you have to stir the water to make sure there's an even distribution of temperature before you actually measure that temperature and measure the EMF. So we're heating the junction in approximately steps of 10 degrees Celsius. And then what we want to do is record the temperature from the thermometer. And the EMF from the voltmeter. Each time. And then we have to make sure that we are asked to draw calibration curve, so I have to state that. So I want to say plot results on a graph of EMF versus temperature. Okay, so we need our fixed cold junction. We need a changing temperature in the second junction. We need to record our temperature and our EMF every 10 degrees. And we need to plot a graph of our results. So we have 3 marks for talking about our hot and our cold junction. 3 marks for talking about heating the water and noting the temperature and the EMF each time. And 3 marks for referring to how we were going to plot that calibration curve. Okay, so this was a full question, so it was a full 56 marks. So you'd be spending just over 25 minutes on this kind of a question. So what I want you to do now is you're going to have a look at some calculations in your textbook on page 166. And I'm going to get you to do question 1, question 2, question 4, question 6, question 7, question 9, question 11, question 12, and question 13. So 1, 2, 5, 6, 7, 9, 11, 12, and 13. And then any issues, just ask and I can do out a video solution for you.